Again, good morning to you all. Now we are going to discuss on some three topics. Just we have three slides in this presentation. Just we are going to discuss on some three topics over here. This first slide, which is about um, the finite automaton, just an overall summary of the finite automaton, and the second slide, which is about conversion of regular expression to finite automata. So to convert the regular expression to finite automata, so what are the rules that we have and how those rules which is been framed into algorithms. So we are going to discuss it with some algorithms. And third one, minimizing the number of states of DFA. So these are the three topics that we have now to discuss. So among these three topics, the last two topics seems to be a very important one, because we could expect that particular question for about 80 percentage. We could expect those two questions, converting regular expression to finite automata, and then minimizing the number of states of DFA. Okay. So this first slide, which is just going to be like an revision for you, because you people have studied all those things for the past three classes. Um, so um, so finite automata machine. So finite in the sense you will have some specific number of steps. That's about finite. Automata in the sense automatically it used to work, and actually which is a machine here, like a machine which is going to automatically work to a particular extent. That's about finite automata machine. So this finite automata machine, which is going to act like a recognizer for recognize the input strings, and which is going to give the answers. The answer which is going to be either what, yes or no. So this particular recognizer, which is going to recognize what input strings actually. Suppose if the input string present, it used to produce the results as yes. Suppose if the input string is not present, it used to produce the results as no. Okay, so you have some three steps over here. The first one which is about input, and next one which is about finite process, and the last one which is about output. So whatever the output that we're going to get. So input, what are the various components that you're going to pass as an input to the machine. uh, those things we used to call as an input. And what are the components that we have in this representation, finite automata. So all those components will be considered as input. Then methods, in the sense we have some functions, inbuilt functions. So using those functions we are going to process whatever the input that you're going to pass to that particular finite automaton. And output, so finally what is the input string that we're going to detect. So that particular input string which is going to act like an output for us. Okay. And here this finite automaton which is going to act like what, which is going to act like prototype for us, prototype for lexical analysis. So for representing the working model of lexical analyzer, this particular finite automaton which is going to act like a prototype. Prototype in essence actually model, a model which shows the processing or working nature of a particular recognizer. Okay, so that's why we are calling this finite automaton as an prototype for lexical analysis. And then here we have things like what we have transition diagrams. So whatever the graphs that we are going to draw, those diagrams we used to call it as in transition graphs. So you will have some graphs like representation graphs, in the sense you will have some movements and you will have some transitions in that particular states, whatever that we have over there. So because of those transitions, we used to call this particular diagrams as transition diagrams. So you'll have some states, within those states you will have some movements. Those movements, to pass some labels, we have some transitions, those movements. So those movements are called as what, transitions. Because of using this particular terminology, we used to call this particular diagrammatic representation as either as transition graph, or else we used to call it as transition diagram. Okay, so you will have initial state, we used to call it as a start state, and then in between and then you have one more thing, final state, as an accepting state. In between this final state and initial state, you're going to have some n number of steps, n number of states. So these are the things that we have over here. And then the output for this transition diagram, so it used to construct a table. So that particular table which used to act like an output for us, we used to call that particular table as a transition table. So the transition table is constructed in a way that how the particular label is moving from one state to another state. Okay, so depends upon the sending state and receiving state. whatever the label is going to detect over there, we used to construct that particular transition table. So in the transition table, in the first column you will have all those sending states, and then at the top you will have the field names, like whatever the label that we're going to pass over there, those labels which used to act like can field names for us. And then under each and every row, each and every record of that particular table, you will have the receiving state numbers. So the first column, field name, you will have the sending state number, whereas and each and every record down to each and every label, you will have the receiving state numbers. So to construct the transition table, we are using this particular diagrams and graphs, and which is going to act like an output for your NFAs and DFAs. Okay. So and then you have two categories as DFE and NFE, and then you people know about the differences whatever that we have in NFE and DFE. Okay, whereas in NFA we used to pass the input string, and the same label it used to pass more than once, whereas in DFA we won't use any empty strings, and then we used to pass a single label only once from one state to another state. So these are some uh, important thing that we have in this finite automata. This particular thing which used to act like an overall summary of your finite automata. Move to next slide, please. Venusri, move to next slide, ma. So here, this is very important question actually. So actually, the question, this particular question, which consists of some 2 to 3 pages of content, but here I have given in some simple way, which is going to be acts like an a summary for us. Further, we used to discuss this particular question with some diagrammatic representation. So actually, this particular explanation for this question, which just acts like an introduction for us, to get some uh, overall process or overall summary of this particular title. I have given it in a simplest way over here. So here we have an algorithm for converting your regular expression to finite automata. So to convert your regular expression to finite automata, what are the steps, or what are the various formats or techniques, or what are the various steps that we have over here to convert a regular expression to finite automaton. And then here we are discussing an NFA alone. So here we are going to convert a regular expression to NFA generally, because the first and utmost conversion is NFA alone, and then only further we used to convert the NFA to DFA. So here we are discussing about how we are converting the regular expression to finite automaton, NFA. So how we are converting, and what are the various formats, or what are the various steps that we have over there. So these are the various steps that we have, and using these steps we would be able to construct an NFA from the regular expression. So you people know very well that regular expression, which consists of what, we will have some operands and then operators. So the combinations of operands and operators, we used to call it as what, regular expression. So in this algorithm you have three things: what, input, method, and output. So the input, which is going to be nothing but whatever the regular expression that you're going to use. So far we have discussed two regular expressions. The first one, which is about a r b to the power of asterisk and a b b. That's going to be the first regular expression, and the second regular expression is a asterisk r b b asterisk. So these are the two regular expressions that we have discussed so far. So the input, which is going to be the regular expression, and method, so whatever the mathematical model that we are going to use over here, those mathematical model which used to act like an method for us. So mathematical logic in the sense, for example, we used to use the mathematical logic like concatenation, association, and commutative. So these are some mathematical notation actually that we're going to use over here. Recursion, so the recursion, association, and then commutative. So these are some various notation that we're going to use, mathematical notation that we're going to use over here. And what is the output that it's going to generate? Generally it's going to generate the NFA as an output. So the input, which is going to be regular expression, and method, the mathematical model, whatever that you're going to use, those mathematical model which is acts like a method for us. And then the output, whatever the NFA that we're going to construct from this, those NFA which is going to act like an output for us. So it's very simple. The first one, the first conversion. Okay, the first conversion that we have over here. So basically, in all these states, so in this conversion, we have some various diagrammatic representations. So in this particular algorithm, those diagrammatic representations are very, very important. Those diagrammatic representation which used to be in the form of NFA, non-deterministic finite automaton. So which is going to be like an NFA over there, where you will have initial state and you will have final state, and you will have some various intermediate states over there. So basically this particular diagrammatic representation, which is going to be what, a NFA, and that's going to be actually the output for this particular algorithm. The first conversion that we have over here, only label, only one label, okay, only one label that you're going to pass. So here the first example here is using one label. So in this slide, in this particular statement, one label n1 comma empty label comma associative comma commutative, and to the last, what we have, last statement, which is about more than once or recursively. Okay, more than once or recursively. So these are the 5 important steps that we have over here in this algorithm. So here in this algorithm we have a total of 5 important steps. The 5 important steps are: the first one, passing the label, only one label alone. Second one, which is about passing the empty label. Okay, and the third one, which is about associative in the sense, here we have what, n1 and n2. N1 which is going to be NFA1, and N2 which is going to be NFA2. So associative in the sense, we are going to concatenate both N1 and N2. That's about associative. So by combining N1 and N2, we are going to generate a new NFA. So that's about associative. And the next one, which is about commutative in the sense, either or, either you are going to use NFA1 or you are going to use NFA2. So you have two possibilities over there, either NFA1 or NFA2. And to the last, we are going to use N1 alone, NFA1 alone, but in that particular NFA itself, we are going to implement the concepts of recursion or recursive nature. So just we have some 5 important steps in this algorithm. So the first step, so in the first step, we are going to have what, we are going to have initial state, and you have an NFA1. Okay, you have n1, n1 stands for what, NFA1, and you have the final state. So you have initial state and you have final state. So for this NFA, you have two states, initial state and final state. So between this initial state and final state, just I am going to pass only one single label. It may be any label. Label in the sense starting from small a to small z. So any character that you're going to pass from one state to another state, that individual character we used to call it as what, label actually. So here in this NFA representation, just we are going to have only two states. Okay, the initial state and final state. Between this initial state and final state, just I am going to pass only one label, only one character. Okay, so this is going to be one of the general form as how we have to use NFA. So this is going to be one of the general form. Okay, okay, and then I'm moving to the next one, the second one. In the second one, we have in the second one we have what, initial state and final state. In this initial state and final state, we are not going to move any label at all. Okay, so that's why we are mentioning it as an empty label. So between the first one and second one, the difference is, so in the first one we are passing what, only one label. So that's going to be the thing that we have in what first example. Just we are going to use NFA N1 alone, where you have what two states over there, and we are going to pass a single label. And now here in the second example, uh, you have what NFA1 with two states. In this, between these two states, we are not going to pass any value at all. So just you're going to pass the empty character that belongs to symbol alone over here. So these are the two examples, two general forms that we have related to conversion of regular expression to finite automata. So it's simple. In both the examples, what we have in both the examples, in example 1 and example 2, you have NFA. Okay, that's why we used to represent it as N1. In both the first example and second example, you have NFA. In both the examples, you have two states. What are the states that we have? You have initial state and final state. That's it. Just you have two states over there. But what's the difference that we have? The first example, we used to pass a label. That too only one label, because we have two states. Between one state and another state, just we are going to pass only one label. Okay, in the second example, we have two states here, initial state and final state. We are not going to pass any value at all, just that's which is going to act like an empty string. So that's it. So these are the two general form that we have. So in the first example, we are passing a label, single label, and in the second example, just we are passing what a empty label. Empty label in the sense empty string, and there is no any label at all. So that's why in this slide I have represented it as was one label of n1 and an empty label of n1 actually. Okay, so these are the basic two general forms that we have over here. And then the third one, so here actually we are using what, here we are using some mathematical model. In the third example, we are using mathematical model named as associative. Okay, and then here the general form is r1 into r2. The general form for this third example is r1 into r2. So in this r1 into r2, we are using two NFAs, n1 and n2. Okay, so this is very very important here. We are using two NFA, and see here this is very important. In NFA you have an initial state, NFA1 you have an initial state, and in NFA1 you have a final state, and in NFA2 what you will have an initial state, and in NFA2 you will have what final state, because for each and every NFA you will have what initial state and final state. So totally how many initial state and final state that we have over here? We have two NFAs, and then in these two NFAs, for each and every NFA what we used to have, we have an initial state and final state. So for NFA1 you have initial state and final state, and for NFA2 you will have what initial state and final state. Together how many initial state and final state that we have? Dear students, answer this question. Give answer to this question. So in this associative law, in this third example, this is going to be third associative, which is going to be third example. So in this example, we are using two NFA. NFA1 that's about N1 and NFA2 that's about N2. For NFA1 you will have what initial state and final state, and for NFA2 you will have what initial state and final state. Now the question is a total of how many number of initial state and final state that we have in this associative law? A total of two initial state and two final state. So both Shruti and Vinusri have answered it. Yes, so that's the answer. That's the right answer. Because for NFA1 you have one initial state, and for NFA2 you have what one more initial state. So 1 plus 1 you have 2, and for NFA1 you have one final state, and for NFA2 you will have another final state. Together you have two final state. So total of two initial state and final state will be there in this associative law. But here in this implementation we are going to change it. How we are going to change it? We are going to change it in a way that NFA1 you will have an initial state, and NFA1 you will have an final state, whereas the final state of NFA1, which is going to act like an initial state for NFA2. Okay, consider or imagine that the final state of NFA1 will be acting like the initial state for NFA2. Okay, so how we are going to do it? The final state of NFA1 will be merged with the initial state of NFA2. Okay, now once again we are going to have what we are going to concatenate actually. So for concatenation purposes, we are going to merge the NFA1 and NFA2. How we are going to merge it? The final state of NFA1 will be merged with the initial state of NFA2. Okay, now the final state and initial state get together, which is going to act like an concatenation operation or concatenation function between NFA1 and NFA2. Okay, here the important thing is we used to pass the label. Okay, we used to pass any label or any number of label, but the condition here is it have to pass through both n1 and n2, and finally it have to reach the final state of n2. Because for n1 you have initial state, but n1 you don't have initial state, because which is going to act like an initial state for what? N2. And for n2 you will have what? You will have an final state. So whatever the label that you're going to pass, it have to pass through both n1 and n2, and finally it will reach the final state of n2, and then it used to produce the results over there. That's why in the general form we have given it like what? R1 into R2. So R1 into R2, which means R1 and R2, like an AND operator. So AND operator, which used to work which used to works like it have to use both N1 and N2. So whatever the label that you're going to pass, it used to pass through N1 and also N2, and finally it used to produce the results. So from the name associative, we come to a conclusion. Here we have to use both the NFAs. Okay, so whatever the label that you're going to pass, it have to pass through both NFA1 and also NFA2, and finally it will give the results, the appropriate results. So that's about associative. Associative in the sense both. You have to use both NFA1 and also NFA2. You have to use both N1 and N2. Okay, so that's the thing. That's the important thing that we have over here. But how we are concatenating? We are going to take the final state of NFA1, and then we are going to merge it with the initial state of NFA2. So there occurs the concatenation. So the final state of NFA1 and initial state of NFA2 will be merged together. So basically you're going to have 3 circles over there after concatenation, because for NFA1 you have what? 2 circles for the accepting state. For NFA2 for the initial state you have what? 1 circle. So now we are going to concatenate the 2 circle with the 1 circle, which is going to act like in single circle over the 3 circles, which is going to act like in a single state over there actually. So whatever the labels that you're going to pass, it have to pass through both NFA1 and also NFA2, and finally it used to produce some results. Okay, so this one which is going to act like what? Which is going to act like an associative, or which is going to act like and work like an and operation. Okay, so that's about the third one, associative, R1 into R2. Okay, and then the fourth one, commutative. Commutative in the sense which is going to work exactly opposite to the previous one, associative. So here what? Either N1 or N2. So that's why we are representing the general form. The general form here is what? R1 or R2, the slash which represent OR operator. So R1 or R2. So here which is going to be in a way that you have both NFA and DFA. See NFA N1 and NFA 2. So you have two NFAs over here. So in this NFA 1 and in NFA 2, you have what? The initial state and final state. So in NFA 1 you have initial state and final state, and then in NFA 2 you will have what? Initial state and final state. Here whatever the empty label that you're going to pass, label that you're going to pass, not empty label, the label that whatever that you're going to pass, the label it used to pass either through N1 or through N2. It's very simple. So whatever the label that you're going to pass to this NFA, it is going to use either N1 or N2, and finally it used to produce some results. But here you don't have any concatenation. We are not going to merge anything over here. the NFA N1 which is going to be in separate one, and NFA2 which is going to be in separate one. So both the NFA which is going to be in a separate fashion, where the label that you're going to pass, it may be an A, B, C, or D, or any label between small a to z, small z, whatever that you're going to pass. It used to use either N1 or else it used to use either N2. Okay, so this particular law we used to call it as commutative law. So this is going to be the fourth general form that we have over here. Okay, and then the last one, what using N1 more than once or recursively. So here in the fifth general form, it's going to be very simple. So you have an N1 or NFA1. We are going to use the same N1 or NFA1 more than once, like a looping process. So normally in NFA we used to use these loops, the same the same state uh, which used to get executed more than once. So these types of loops may occur in NFA diagrammatic representation. So here you have what NFA. In this NFA, what you will have initial state and final state. We could consider in a way that between this initial state and final state, you may have one more state, or else the initial state itself, which is going to be the state which is to work in a repetitive manner, which is going to work in a recursive manner, or else the final state itself, it used to work in a recursive manner, or the state which is in between the initial state and final state, it may work in a recursive manner. Recursive in the sense the same label it used to pass between the same states more than once. So from 0 to 0 itself, suppose you're going to pass the label A more than once, which used to call it as an uh, recursive nature. Okay, so that's why we are representing what or asterisks. So normally in an expression, in a regular expression, we used to use what the asterisk as an option to represent what, to represent the repetition of the same label, or the execution of the same label, or the transition of the same label more than once. So in the earlier examples, a or b to the power of asterisk a b b. So in this regular expression, what we used to do, we used to take the label a or label b, and the label a and b, it used to move to the same state more than once. So the first NFA diagram, from 0 to 0 you will have the movement of a, and 0 to 0 you will have what, the movement of b. So ARB asterisk, to represent that ARB asterisk in an NFA, you will have a state what, state number 0, the initial state. To the same state, 0 state, from 0 to 0 itself, we used to pass A, and also we used to pass B. So those types of representation, moving the same label more than once, using the same state, in the same state, that particular representation we used to call it as a recursive nature. Okay, so here they have mentioned it as what, using N1 more than once or recursively. So using a particular state of the N1 more than once or in recursively. So these are the five important general form that we have over here in this conversion of regular expression to finite automata. For each and every general form, we have some simple diagrammatic representation. So in the upcoming classes, I will explain the same concepts using diagrammatic representation. So while discussing with diagrammatic representation, you will get some clear idea. Okay, so now this is going to be, which is going to act like an introduction class for this particular regular conversion of regular expression to finite automata. So a total of how many forms, general form that we have over here? We have a total of 5 general forms. The first general form, what we are going to do, we are going to pass a single label. The second general form, what we are going to do, we are not going to pass any label at all. So we used to call it as an empty string. That's going to be second general form. The third general form, what we are going to do, we are going to use the law named as in what, associative law. So in this associative law, we are using the general form r1 into r2, or else we used to call it as n1 into n2. So here we have to use both n1 and also n2. So whatever the label that you're going to pass, it have to pass on both n1 and n2, and finally it have to produce some output over there. So this is about associative in the sense R1 into R2 are both, the meaning for associative is both, so we have to use both NFA1 and NFA2. Okay, and the fourth general form is what we used to call it as an commutative in the sense which used to works like an or operator. And then here, what is the general form that we have? R1 slash R2 or R1 or R2. So R1 which represents some regular expression 1, R2 which represents some other regular expression. Here we have two NFA, NFA1 and NFA2. So here, either we are going to use NFA1 or else we are going to use NFA2. So you have two pathways over here. A label may pass through either the first path or else it used to pass either through the second path. So it used to pass through NFA1 or else it used to pass through NFA2. So these types of transitions we used to call it as an commutative. Okay, or else we used to call it as an either or, either N1 or N2. Okay, and then the last fifth general form which is going to be recursive procedure, where you will have a single NFA and you have some states in that particular NFA where the same state which will be used more than once repetitively. Okay, the same state which has been used more than once repetitively, or else the same label will move within that particular state more than once. So this particular representation we used to call it as a recursive procedure. So a total of 5 general forms that we have. The first one which is going to be with single label, and second one without any label, a third one using AND operation using both NFAs, and fourth one using either N1 or N2, and fifth one using recursive procedure. So these are the 5 important general forms that we have in the conversions of regular expression to finite automata. Okay, um, okay. Um, the next topic is minimizing the number of states of DFA. So this is going to be one of the important topic, and then for this too we have some diagrammatic representation. In the next class I will explain about this particular topic with some diagrammatic representation. Now we have some 10 more minutes. Within this 10 minutes I would like to give some basic introductions on this minimizing the number of states of DFA. Okay, so here, what we are going to do, we are going to minimize the number of states of DFA. Our objective here is what? We have to minimize the number of states of DFA. That's the objective. And then, what is the purpose of this objective? Why we have to minimize the number of states of DFA? So we have DFA, and then DFA which is going to have some n number of states. For example, the DFA 1 which is going to have some 10 states. And then what we are going to do here, we are going to minimize the number of states. So either we have to minimize the state number from 10 to 9 or 10 to 8 or 10 to 7. So we are going to decrease the number of states of DFA. So it's very simple. So this particular topic which deals with how to minimize the number of states of DFA. So in DFA to the maximum you could have some 10 states or 12 states. It depends upon the DFA that you're going to construct. For example, in your DFA you are going to have some 5 states. For example, S0, S1, S2, S3, S4. So like that you're going to have some 5 states. Or else we used to represent the state numbers as 1, 2, 3, 4 or 0, 1, 2, 3. So like that we used to represent the state numbers. So for example, in DFA1 you're going to have some 10 states. We have to reduce the 10 states either to 9 or 8 or 7. So based on the requirement or how or based on some procedures or based on some needs, we are going to minimize the number of states of DFA. Okay, and here we have some algorithm actually. So using that particular algorithm, we are going to minimize the number of states of DFA. So in this algorithm too, you have some 3 things as input, process, and output. So input in the sense, so whatever the DFA that you're going to minimize in terms of the number of states, so we are going to pass that particular DFA as an input. For example, DFA D1, which is going to be acts like an input for us. And then what is the method that we're going to use over here? The method that we're going to use over here is we have some algorithms. So we have some functions. Using those functions, using some condition, we are going to minimize the number of states. So the condition which is going to be in a way that For example, suppose in DFA D1, suppose if the same work which is been performed by two states, which has been reduced to one state. It's very simple. Suppose if the same work which has been performed by two states in DFA1, which will be reduced to one state in DFA2. So this particular DFA2 which is going to act like an output for us. Okay. So it's very simple. What is the method that we are going to use? The method that we are going to use here is which is to work in a way that suppose in DFA D1, suppose if more than one state which is going to do the same work, okay, those number of states will be combined into a single state. For example, DFA D1 which is going to have state numbers 1 and 2, these 1 and 2 which is going to work in a similar fashion, which is going to do the same work. And then normally what we used to do. So why these both these two states have to work in a similar way, or which is going to produce the same output actually. So instead of using the two states 1 and 2, which is being combined into just one state. Okay, so these two states number 1 and 2 in DFA1 will be converted to just one state in DFA2. So the DFA2 which is going to act like an output for us. So this is going to be the overall story as how we are going to minimize the number of states of DFA. So here I have given some examples that sometimes for the same process more than one DFA could be represented to recognize the same string. So you have a regular expression. To that particular regular expression, we would be able to construct two different NFEs. Okay, for a single regular expression, we are going to construct some two different NFEs, DFAs, not NFEs, DFAs. So DFA1 and DFA2. Now the DFA1 and DFA2, which is going to produce the same output. Okay, and here the DFA1 which is going to be with some 5 states, and DFA2 which is going to be with 3 states. And now generally which DFA that we would prefer? So normally here we used to prefer the DFA2 because which is going to have some minimum number of states. Okay, whereas DFA1 which is going to have more number of states. Okay, so that's what they are describing over here. For the same process we could construct more than one DFA. Among those more than one DFA which is going to have the minimum number of states, and one DFA which is going to have some more number of states. But our preference as per the need, as per the requirement, we are going to consider the DFA which is going to be with some minimum number of states. So for the same regular expression, whatever the DFA which is going to produce the minimum number of states, DFA with minimum number of states, that will be simulated into a program. Okay, and whenever the minimum number of states DFA which is simulated into a program, which used to construct, or which used to produce some minimum number of lines of code, so that which used to work in a very efficient way comparing to the DFA which is going to have more number of states. Okay, so that's the thing. So which has been represented to recognize the same string. Here we have two examples, one with 4 states and another with 5 states. So here one DFA which is going to have 4 states, where another DFA which is going to have what, 5 states. So what we are going to do in this situation, so we are going to choose the states, and we are going to choose the DFA which is going to have minimum number of states. So whatever the DFA which is going to have with minimum number of states, that will be chosen. And then so that's going to be the optimum procedure whatever that we have to follow. So it is going to be like this. So for example, you're going to travel from one source and destination. Between source and destination, suppose you're going to have 4 signals, and you're going to choose another path, where in that particular path you're going to have what, just 3 signals. So which path that we used to prefer? We used to prefer the path which is with some low signals, which is with some less signals actually. Okay, similarly here we are going to choose the DFA which is going to have some minimum number of states with it. Okay, So finally what? So to find the states which repeat the same work to be identified and combined into one state. So this is the actually method that we are going to use. In this method, we are going to find out the state which is repeating the work. For example, if two states are doing the same work, we are going to merge those two states into one single state. Okay. So repeat the same work to be identified, and we are going to combine. That's about merging. So we are going to combine into some one state. So automatically we are going to reduce the number of states over there. Okay. Mm, so this is what I want to explain to you people. Move to next slide, ma. Okay, so which is actually we are completing this presentation. Before closing the session, I would like to ask a few questions to you people. Okay, the first question is, so how many number of general forms that we have in the conversion of regular expression to finite automata? So how many general forms that we have? How many general forms that we have in the conversions of a regular expression to finite automata? So how many that we have? I am receiving so many answers. Very good, very good. So the answer is 5. Who answered it first? Ministry have answered it first, and then Jodi, and then Sindhu, Pravina, Deepika, Shruti, Rohit, Balaji, Meghana, and Manjula. So this is the right answer. The total number of steps, that total number of general forms that we have in conversion is a total of 5. Okay. So in those conversions, in those general forms, we have some two laws actually. So what is the law name that we have used for the third general form? For the third general form, we used to use the law. What is the law name that we used to use? So associative is the law that we are using. So Shruti, and then Venusri, Deepika, Induja. So many of them are answering. Okay, good, very good. So the third general form, the law that we are going to use is what? Associative law. Okay, and then the next question. So what is the fourth general form law? What is the fourth general form law? So what is the law that we are going to use for fourth general form? So answer is very right. The answer is what? Commutative. So Deepika and Venusri, and then Shruti, and then Sindhu and Darshini. Okay, and then Meghanathan. So most of our answer, and Jyoti Kumar, and then Pratish. So most of you have answered it very correctly. So the fourth general form law is commutative law. Very good. The last question. So in the last topic, minimizing the number of states of DFA. Okay. Um, so what is our objective? What is our objective? What is the objective of minimizing the number of states of DFA? What is the objective of minimizing the number of states of DFA? So what is going to be the objective? Minimizing the number of states of DFA. Or else, why we have to minimize the number of states? To reduce the number of states. Okay, good. Actually, we have to reduce the number of states of a DFA. So that's going to be the right answer actually. Okay. So the objective here is what? To reduce the number of states of DFA. This is going to be the exact objective. So if five states in N1, then we have to reduce 2, and the mechanism have answered to reduce the number of states of. So that's the answer actually. Okay, to reduce the states of DFA. Okay, so in minimizing the number of states of DFA, the objective is we have to reduce the number of states. Okay, so that's the right answer. So most of you have answered it right. So thank you, students. Thank you for listening listening patiently and answering my questions. So thank you, students. Thank you for listening. Thank you.